Hello again, folks. We are going to continue on to Chapter 3 with Section 3.4, Inverse Functions and Relations. So, with no further ado, let's get over to our notebook. All right. So, with an inverse function or relation, this goes back to our discussion earlier in the year about what is a function versus a relation. Relation is that bigger set that relates one variable to another, those equations that do that. Excuse me, where functions, on the other hand, are those ones that have that special relationship for each x, there's one y. They pass the vertical line test graphically, all that stuff that we discussed before. I want to get into more what an inverse is. I know you guys have had some experience with inverses, but I don't think often you understood what they do. The idea of an inverse is pretty straightforward. It's the idea that if I have a normal function, I take x and I put it into this machine we call f, right? A function f. When it comes out of that, it is an f of x, right? So for example, if I had the function f of x equals just something basic, 3x plus 2, and I put x equal to 1, then f of 1 is 3 times 1 plus 2, that's 5, right? So what that's saying is I take 1, I put it into my function f, and it comes out as 5. Now, what the idea of an inverse is, an inverse relation or function, is that we take f of x, the result of that function, and we put it into this thing we call f inverse. We note that, or denote that, with f to the negative 1 power. That means f inverse is how we read it. We put it into f inverse, and f inverse would give us back our x. So if we took 5 and put it into the inverse relation or function, it would come out as 1. You get back your original input. So in other words, your domain for f kicks out these range values. The range values in the inverse are the domain, and they give you back the domain values for the original function. So what you see is the domain of f is the range of f inverse, and the range of f is the domain of f inverse. All right, they reverse roles. So we're going to get into, in a short amount of time, how we find the inverse functions. But right now, I just want you to understand that there is this relationship. Now, if you have an original function, its inverse may not be a function. All right, if your original process f is a function, the inverse may not be. I want to be clear on that. It may just be a relation. It may not pass the vertical line test, and vice versa. You may have something that does not pass the vertical line test is the original function, but it does as its inverse. All right, so those things are possible. So let's look at a little more about this type of thing. I have a grid here because the type of questions they're going to ask you could be something like this. They may ask you to graph each function and its inverse. Now, I'm going to write this out first. Each function and its inverse. Notice they just say it's inverse. They don't say it's inverse function. It could be an inverse relation again. All right. And they may give you something. Let's do this one. F of x equals x minus 2 squared plus 1. All right. Now, notice I said we're going to talk later about how to find the inverse. So we don't know the inverse of this function, but we know the function. And I want you to think to what I just said. We know that for this function, it has a set domain. The domain of this is all real numbers. It also has a range that is all real numbers. Actually, I'm sorry, it's not. It has a domain that would be, well, let's look at this function first. Let's just graph it. We know we're moving right 2 and up 1, right? Just from the previous units we've done. We know that this is a squared function. That's the parabola pointing upward. That's moved right 1, shifted right 1, or translated right 1, or right 2 and up 1. So we've got this. And then it goes over 1 up 1 in each direction, over 2, and up 4, and we can get a decent sketch, whoops, of this graph. Let me do that better. There we go. Whoops, I skipped it. I was lifting too lightly. All right. So we have that point. I'm putting known points here because I want us to be able to use these for the inverse. All right, so we have this function. We know that this function has a domain of all real numbers. Its range is y greater than or equal to 1. That's just the fact of what we see. Now we know the inverse function will have the opposite relationship. Its domain will be x greater than or equal to 1, so it'll just be these x's. And its range will be all real numbers. All right, now, how does that work? Well, one really nice relationship between a function and its inverse is the graphical relationship they have. And that relationship is that for this line, let me do this, there and there. For the line, if we draw the line y equals x, every function's inverse, I should say, whoops, I don't want that, is a reflection across the line y equals x. This is the line y equals x. All right, every function is a reflection, because think of what happens. In f of x, I get x, y. Well, in f inverse of x, what happens? The y becomes the x value, the x becomes the y value. In our symmetry unit, didn't we talk about that being the symmetric relationship? If AB is on the graph, then BA is on the graph, was those functions that had symmetry across the line y equals x. So when we see this relationship here where all the points on this are reversed in this, that has the same type of thing. It's not called a symmetry, but it's a reflection across the line y equals x. So any point we have here, we can reflect just by reversing it. This is the point 2, 1. So the point 1, 2 will be on the reflection. The point 3, 2 graph on the original graph. So 2, 3 is going to be on the reflection. The point 1, 2 was on the original graph, right? So 2, 1 will be on reflection. Do you start to see what's happening? If I go to 4, 4, 5, then 5, 4 will be on the graph. I had 0, 5, so 5, 0 will be on the graph. Right? And we get this as our f inverse. All right, this was our original function. If you're ever asked to do this, make sure that you do what I just did, that you label them which one is which. All right, if it says graph each function and its inverse, don't just throw two graphs down on a piece of paper. You don't necessarily have to draw the line y equals x. I just wanted you to see that it is a reflection across that. If you think of the original point here, the new point was straight across, right? This point became that point, and so on. This point became that point. This point became that point. You see how those relationships held, all right? It is a line y equals x, but you do need to be able to draw those graphs. All right, so if they ask you to graph a function and its inverse, and they only give you the original function, don't solve for the inverse. Just draw the graph and reflect it. Save yourself time. It's much quicker. All right, that's the first type of thing we're going to deal with inverses. And this is just building some background information. You now should know what an inverse does, how it reverses domain and range in a function. And you should know that a function and its inverse are just reflections across the line y equals x. So now we're going to get to that I guess procedural thing of how do we find the inverse function. All right, so let's look at that. Let's do this one. Let's say, all right, it says find the inverse of f of x, then state whether the inverse is a function. By the way, that brings me back to another point here when we ask whether the inverse is a function. Let's look back at that last one. The original function, f of x, was a function, right? X minus 2 squared plus 1. It's a quadratic. It's a parabola. It's a function. It passes the vertical line test. But its inverse is not a function. It's just a relation. Its inverse does not pass the vertical line test. All right, so it's something to be aware of. All right, so let's start this next process with that function. Let's do our first example as f of x equals x minus 2 squared plus 1. Let's find this inverse. And I'm going to break this down into steps for you guys. The first step, I'm just going to say y equals. You want to change this f of x to y equals. All right. And this is just a procedural thing I've found over the years that makes it easier to see for you. All right. The second thing, switch y and x. Now, when I say switch y and x, just where you see an x, make it a y. Where you see a y, make it an x, anywhere in the function. So this becomes x equals y minus 2 squared plus 1. Okay? So now what do we do? Well, now we solve for y. All right, third step, solve for y. All right, so now solving for y, I got to get y by itself, so I got to get rid of this first, subtract 1. X minus 1 equals y minus 2 squared. Well, we just did this quadratic thing, right? So let's solve this. We take the square root of each side. Remember, when we take a square root, we got to consider plus or minus square root of x minus 1. I can't do anything with that. This side becomes y minus 2. What do I do with that? Well, I'm solving for y, so I get y by itself by adding 2 to each side. So I would get 2 plus or minus square root of x minus 1 equal to y. And that would be my f inverse. The inverse relation would be y equals 2 plus or minus square root of x minus 1. And notice I called it an inverse relation, right? F inverse would be y equals 2 plus or minus square root of x minus 1. So that's the process. Write it as y equals, switch y and x, solve for y. Let's do another one. All right, let's do f of x equals, oh, I'm sorry. I said it, but I didn't write it. Part of our solution, it says state whether this is a function. So the next part of that, you should have said not a function, right? Make sure you always answer the question. I always make that a big deal in class. I should have done that there. I apologize. All right, so we have that. Now let's go back to what I was going to write. Next question. Let's try the same thing again. Find the inverse. State whether it is a function. Let's do this one. Yeah, we'll do that. All right, so again, follow that process. The cube root of x minus 3. Then we switch x's and y's. X equals the cube root of, sorry, y. I did write a y, but it doesn't look nice. Y minus 3. Now, to solve for y, I got to get rid of this cube by cubing this side, so I cube this side. And I get x cubed equals y minus 3. Add 3, I get x cubed plus 3 equals y. And I have my function. Let's see. So we have our inverse function. Now I said this is a function because I know something about x cubed. X cubed plus 3 goes up 3, and it does that, right? It has that symmetry with respect, well, the symmetry with respect to the origin. This will have symmetry, rotational symmetry about the point 0, 3. And it does pass the vertical line test. The original function was doing this. right? That would have been f of x. This is f inverse of x. They are both, in this case, is functions. So this is, what was I writing there? Oh, this is a function. All right. And there are some, this may seem straightforward. You may remember doing this at some point, but there are some of these functions that are a little harder. And I'm going to give you one just to also demonstrate the need to find some old stuff and use it. All right, so if you were given f of x equals 2 over x squared plus 4x. So let's follow our steps. Again, there's no reason not to be able to follow the first couple steps in this process because you don't have to look at it, guys. I say this again and again in class. Trust the process, all right? Don't try to solve these problems in your head before you write anything down. Just start in, all right? It's something that, again and again, I find working with students that are struggling. They stare at a problem and don't move. You have steps to these problems if you've been following along, so just follow the steps. Write it as y equals. Switch any x into a y, any y into an x. So now I get y squared plus 4y. Now I need to start thinking about how to solve this. And one thing I want to remind you is if you have a equals b over c, that's equivalent statement is c equals b over a. In other words, we can switch these two items, right? Technically, we're multiplying by c, getting that on both sides, then dividing by a, but it turns out to be this. So you can just switch these when you have this. Well, that's what we have here. We have this quantity and this quantity that we want to switch. So I want to say y squared plus 4y equals, and that would be 2 over x. And we're solving for y, remember. So I've got this now. Now, this is where people just lose it because they're like, oh, all right, so now I'm going to try to get rid of y. Well, how am I going to get rid of y? I've got y in two different statements. If I factor out a y, I get y times y plus 4. Still have two different things. I need to be able to get to a single y. Guess what we're going to do? Whoa, not that. Not scribble all over a problem. We are going to do CTS, complete the square. What would I need to complete the square on this side? Well, take half of that and square it. I'm adding 4. I add 4 over here. So now I can write this thing as y plus 2 squared. For all those that were saying, well, I don't need to learn completing the square. Yes, you do. We're using it again. Remember, I promised you we'd use it a couple more times. This is one of them. So now I have that equal to 2 over x plus 4. Now, what do I have to do? Well, I got to get y by itself. So I am going to take the square root of this side and the square root of this side. On this side, when I take the square root of that squared, I get y plus 2. On this side, I get plus or minus the square root of 2 over x plus 4. And last thing, subtract 2. I get y equals negative 2 plus or minus the square root of 2 over x plus 4. And again, with this, when you see a square root of a quantity and a plus or minus, this is not going to be a function. So we get this, not a function. All right. And again, just a nice demonstration of where else we could use completing the square besides solving a quadratic. We can use it to find an inverse given that situation. All right. Almost done. One last thing that I want to cover, and that is this idea. All right. Given f of x equals, let's just say, let's do a basic one, 5x plus 3. Find f inverse of x. And it may say verify, it may say show, it may say prove. Yeah, that P word you guys all hate. It may say any of these things, verify, show, or prove that F and F inverse are inverse functions. All right. This goes back to that definition. All right. When we verify things, we often go back to definitions. And this is one of those. The definition of an inverse is if two functions, or by definition, it states that if two functions, call them f of x and f inverse of x, are inverse functions, are inverses, I'll say, then two things have to be true. First thing is that f of f inverse, that's supposed to be an open circle, f of f inverse of x, I can't stand seeing that by the way, f of f inverse of x equals x, and two, f inverse of f x is equal to x. So we have to show that. We have to prove this, that once we find this inverse, we have to verify or prove by using this definition, by doing the composition both ways. So again, something else we've done this year that we're going to have to use again, that composition of functions. So let's start. First step in this is we were given f of x equals 5x, I forgot, plus 3? Plus 3. All right, so plus 3. So what does that mean? I need to start by finding the inverse. So y equals 5x plus 3, x equals 5y plus 3. First two steps of finding the inverse, right? Now I solve. Minus 3, I get x minus 3 equals, excuse me, 5y. Divide everything by 5, and I get that y equals x minus 3 over 5. And I'm going to leave it that way. You could call it 1/5 x minus 3/5. If you want to do that, that's fine. We followed and done the first step. Now we have to prove that this is the inverse, right? So we've got f of x equals 5x plus 3, and we have f inverse of x. And these are both functions, so I can use this notation. That is x minus 3 over 5. So now I have to prove this. So the second part of this problem is to verify, show, or prove, however they state it, that these two are inverses. So I need to do f of f inverse of x first. And that's going to be equal to f of f inverse of x, which is f of x minus 3 over 5. Again, I'm just doing this in small steps so you can see what I'm doing. And that means I plug this into f of x. So I need 5 times this thing plus 3. So what happens? 5 times this, these cancel, right? Because this is 5 over 1 times something over 5. That cancels, leaving me x minus 3 plus 3. And you need to show this, guys. You need to show each step in this. And that means it's x. So we've got a check mark here. First thing, prove true, that f of f inverse gave us x. We're not done, though. We have to prove both directions. So the second part of this is to do f inverse of f of x. So again, just to clarify notation, this is that, which is f inverse of 5x plus 3. So that means I take 5x minus 3 and put it in for x in x minus 3 over 5. And again, I don't want to see all sorts of cancels all over the place. Write out each step at each time. First thing that would happen here is, I'm sorry, this is 5x plus 3. 5x plus 3 minus 3 is 5x over 5. And then these would cancel, leaving x. We've got our check, and we've proven it. These two, that's all you need to do to prove, show, or verify that those two are inverses. All right, and that's the only way. Every year I'll have people go through and say, all right, well, I'll just solve backwards and show that when I get the inverse of the inverse, it's the original function, and that proves it. It doesn't. This proves it. This uses the definition and proves that those two functions, the one we were given and the one we solved for, are in fact inverse functions. All right, that's in this section. They are going to ask you to do some translating of parent graphs, just some more practice with your graphing. That's pretty much all it's doing. It's going to be asking you to graph some of these and move them around a little bit. All right, other than that, that's this section. That's 3-4, guys. Have fun with it, and I will answer your questions tomorrow. Have a great day.